solution for unsteady state. Based on this diffusibility equation, we can see from here there are two conditions. The first condition is initial condition, and the second condition is boundary condition. Initial condition state that reservoir pressure is at uniform pressure at the beginning of production, while for the boundary condition, the first boundary condition state that they are produced at a constant production rate. And the second boundary condition state that the reservoir is infinite in size. From these conditions, they have come up with two solutions. The first solution is constant terminal pressure solution. We can call it as CTP. And the second solution is constant terminal rate solution. We call it as CTR. For constant terminal pressure solution CTR, we can see from the name itself, the pressure is held constant while solving for accumulative flow. And this solution is applied on water influx and gas oil reservoir. This is the image of water influx. While for CTR solution, constant terminal rate solution, flow rate is held constant when solving for pressure change in radial system. These solutions are commonly used in two forms. The first form is EI function solution, and the second form is dimensionless pressure solution. We call it as PD. So for this video, we will be talking about EI function solution.
Let's elaborate further on EI function solution. So basically, there are 5 basic assumptions when EI function is applied. We know that the first one is the well producing at a constant flow rate, and we know that the reservoir is at a uniform pressure. Thirdly, we also know that the well is centered at a cylindrical reservoir radius, which is called the RE, with the well bore radius, which is dubbed as RW. We also know that there is no flow across the outer boundary, and there is an infinite acting reservoir. So an equation for a pressure P at a certain radius R and a certain time is given as equals to the initial pressure plus 70.6 times the oil flow rate times with the oil viscosity and the oil formation volume factor divided by the permeability, the thickness, and also this equation itself is called the line source. And we know that the exponential integral is defined by this equation, which E would be integrated to become this. The conditions are applied for the line source solution. If x is less than 0.01, then EI minus x is equals to ln 1.781 times x, where x is dubbed as 948 mu porosity, total compressibility R squared over KT. When substituted, a new equation is formed. This new equation would be used also to find the bottom hole flowing pressure. But the formula is not applicable to use if T is more than 9.8 times 10 to the power of 4, porosity, viscosity, total compressibility, radius to the power of 2 over permeability. If x is between 0.01 and 3, then this equation is applied. Instead, when x is between 0.01 and 10.9, then a table or graph can be used to calculate EI. The third one is if x is more than 10.9, then we can conclude that EI is equals to 0.
Now, let's do the example. An oil well is producing at a constant flow rate of 300 STP per day under unsteady state flow conditions. The reservoir has the following raw and fluid properties. The oil formation volume factor is 1.25 billion barrel per STP. the permeability is 60 millidarcy, the porosity is 50%, the viscosity is 1.5 centrifuges, the thickness is 15 feet, the wellbore radius is 0.25 feet, the total compressibility is 12 times 10 to the power of 96 per psi, and lastly the initial pressure is 4000 psi. Next, calculate pressure at radius of 0.25, 5, 10, 50, 100, 500, 1000, 1500, 2000, and lastly 2500 feet for 24 hours. Then we plot the results as first pressure versus logarithm of radius and pressure versus radius. Now let us see the solution based on question given. Step 1. From equation below, pressure at any distance r is calculated as pressure in terms of RT is equal to Pi plus 70.6 Q naught mu naught du naught over KH times EI 948 times porosity mu naught CT R squared over KT. All the informations are given in the question, so we just need to key in the value to get the value of the pressure. Next, we move to step 2. The step 2 needs us to perform the required calculation after 24 hours in the following tabulated form. First, we need to find the value of x based on the radius given using this formula, which is x equal to 948 times porosity mu CT R squared over KT. For the green part, the value of x is less than 0.01, so this equation is applied. While for the yellow part, the value of x is between 0.01 and 10.9. So we need to refer the table to find the EI value. And lastly, for the red part, the value of x is exceeding 10.9, so the pressure value is automatically equal to 0. Now, I will explain to all of you how to get the value of EI by using the table. We take an example. We choose the value of x of 0.0178. Now, referring to the table, we will round off the 0.0178 to 0.018. So, we can get the value of EI is 31458. After we have done the calculation part, we must show the result in a graph form. First, we plot a graph of pressure versus logarithm of radius, where the y-axis is a pressure in a unit of psi and the radius is at n-axis, a unit of feet. Next, second graph is pressure versus radius graph, where the y-axis is a pressure and the x-axis is the radius. Now, we get a graph in the form of this.
As we move on to the next example, using the data in the previous example, estimate the bottom hole flowing pressure, which is PWF, after 10 hours of production. For the solution, step 1, equation 1 can be used to calculate PWF only if the time exceeds the time limit imposed by equation 2, or this is the equation to calculate the PWF. Next, this is the formula to calculate the T. So, after calculating the time, we get 0.000267 hour, or we can convert it into the second, which is 0.153 second. In step 2, since the specified time of that hours is greater than 0.000267 hour, the bottom hole flowing pressure can be estimated by applying equation 1. The final answer, which is our bottom hole flowing pressure, is equal to 3,358 psi.